Good morning, everyone, and welcome to this Greener webinar. Thank you so much for joining us today. My name is Rutger, and I'll be your host. With these sessions, we really want to help you navigate the world of mobile battery power because we want to show you what's possible and, more importantly, how it all works in practice, of course. And I think the recent increase in diesel prices just goes to show that batteries are becoming more relevant than ever. So I would say it's a perfect time for a switch. And we're here to assist you with exactly that. Because today we're going to give you some real insights into the power setups that we see most frequently in the field. So you can get a much better understanding of how these smart batteries actually work in practice. At the moment, we're already seeing this massive shift towards battery energy storage systems. And before we dive into the actual setups, it really helps to look at what's driving this shift in the first place. And in our experience, it's mainly caused by these four main challenges. So first of all, the grid is becoming a real bottleneck in a lot of places across Europe. And that's because demand is growing so fast with electrification going on, but the grid just isn't keeping up. And this leads to all this congestion and these long waits for new connections. Then, of course, there's the geopolitical side, and that's become really obvious lately. But the last few years have been such a roller coaster that it's shown us how quickly energy supply can become uncertain. So energy security has become a huge priority for businesses lately. And on top of all that, you've got sustainability regulations getting stricter. So it's not just about hitting targets anymore, but it's also about learning to operate under these new constraints and managing energy way more efficiently. And all of this leads to rising energy costs, of course, which makes it even more important that your power is managed as efficiently as possible. You can really only do that if you're taking back control, which is exactly where battery storage comes in, because it gives you that autonomy to manage things on your own terms. And that really brings us to what we're here to talk about today, because taking back control is all about how you actually design and optimize your setup. So today I'm joined by our system specialist, Robin, and our technical sales specialist, Nathanaël. And they're going to take you through the power setups that are most common, like peak shaving and grid boost, for example. And they'll be showing you exactly how those are applied in real life scenarios using our EMS in a short for energy management system. And of course, we would love to hear your questions as always as we go. So you can just drop those in the chat at any time. We'll try to answer as many as we can at the end during our live Q&A session. But before we dive into the technical details, it helps to know a bit more about what we do at Greener, where we're currently operating Europe's largest fleet of mobile batteries. We've got 250 units now active across 14 countries. And you will find our systems in three main markets: construction, events, and grid support. Basically anywhere you need reliable power, but emissions, noise, or grid capacity are a constraint. And just in 2025 alone, these systems have already helped avoid 20,000 tons of CO2 emissions. But what really sets us apart isn't just the size of our fleet, it's the intelligence behind it all. Because every project is supported by our energy management system, which enables real-time monitoring and data-driven decision-making at scale. Because at the end of the day, intelligence in energy requires both hardware and data working together, which today's session will explore as well. So with that, I will hand it over to Nathanaël.
Thanks, Rutger. So before we actually want to dive into the standard setups, I first want to give you a brief explanation how the battery works and how our EMS works. So I've got here a picture of how the battery looks inside of the container. We've got our DC batteries where the energy is being stored. Then we have our main inverter over here. And we have our outputs on the right side over here. The outputs are here on the power logs on our mobile 2.b systems, which are our older systems, and on their newer systems, they are over here. And we have the input side over here, and you can see these are the ones on the left here, and on the newer system, they are on the right here. So these are a bit more about the connections. Then how does the system exactly work? The battery measures here and here what kind of power is flowing. So let's say if on the left side there is 50 amps maximum available, the battery measures that, and then on the right side we have, for example, 100 amps of load. The difference then comes from the battery and the inverter. So the inverter will deliver the extra additional 50 amps to the load and makes up the difference between what's going on the input and what's going out on the output. Then we have one additional inverter in the orange over here. That's only on our new systems, which is an inverter that's directly on the DC bus. So this is the DC bus. So it's independent from what's happening over here. Then an additional asset we have is our energy meter. This is an external energy meter we use for some of our standard setups as well. We will dive into this deeper later. Then we also have our EMS. So we've got our hardware part, which I just showed you, that's in our batteries, but we also have got our EMS part. So that's in our greener eye. This is our hardware part, and the software is on this. Our software basically does three things. It does monitoring, alerting, and reporting. So we gather all the data, then we show it in our software, which also creates alerts if something is wrong with the system or somewhere else. And we can get insight in the data that's going on the projects. So we can see what the load is, we can see what the voltage is and everything else. And we also can generate reports to show how much diesel we saved. Now I'll be handing it over to Robin to talk a bit more about the standard setups.
Hello. So I will be telling you about three standard setups. I'll begin with our hybrid and our peak shaving setup. The difference is mainly where the energy is actually coming from. In a hybrid system, we use a switchable power source, which needs to be at a specific load in order to be efficient. Could be a generator, could be a hydrogen cell, could be anything else. And then our peak shaving is when we have a constant power supply and we wish to keep the battery as full as possible and then add the energy from the battery when it is required. So as Nathanaël just explained, for instance, if the load exceeds the maximum rated input or a power source, then the battery will add the difference. And then when the load disappears again, it will draw the excess energy into its storage. And then when the storage is full, it will drop the load on the source again. Usually the source is a grid connection. So hybrid, as I explained, a source could be a generator. So hybridization of a generator is always hybrid, meaning two things cooperating together, and then supplying together our load with energy. So one of the jobs that we did last year is our MRI CTI scanners. So we have for the people who have been with us more often than once have already seen this one pass by. So we had a interesting job where there were a couple of CT scanners which have high inrush currents due to the energy exciting of the magnets upon start, and then that drops away again very quickly once they are energized. When we first encountered this setup, or when the question came to us, there was a 300 kVA generator running for the entirety of the open hours when the scanners were supposed to be available, with a lot of stand down time. and being very inefficient. There was also 125 amp three-phase connection available, but this was not powerful enough to actually support the inrush of the system. So we stuck one of our batteries in between the generator and the load, and thus having a hybrid situation as follows. And then they also added a second MRI CTI scanner to the system. Well, after a little while, we had a look at the data, and we saw that the average power was far below the 125 amp available connection which was there in the yard. So this is where we then suggested, well, maybe we use the 125 amp connection, and then we can take away the diesel generator entirely and just use the grid, which when you're at the hospital maybe is a very good idea to keep the noise down and some of the emissions down. So this is exactly what we did. And then in this manner, we were able to go from a 12-hour running generator to a 0-hour running generator in a couple of steps. So that means that we went from a fully utilized generator, or generator running all of the time, to a hybrid setup, which then went into a peak shaving setup. So that means that, as soon as we went into the peak shaving period of this project, we had, of course, 100% saving on diesel costs and CO2. And then for the interested among us, there was some, in the hybrid situation, we saved 56% of fuel and 87% of running hours. Well, whoever is running a fleet of generators will be interested to see that saving nearly 90% on running hours will extend your maintenance runs substantially in the future. So I'll hand it back to Nathanaël, who will tell you a little bit about our load sharing setups.
All right. So like Robin said, he's been talking about peak shave and a hybrid solution. But let's say your grid is doesn't have enough capacity, so kilowatt hours, to supply the full load. You need an additional power source, which in this case could be a generator. So what we do is we use the grid. We use it at its most efficient rate, and all additional energy we use from the generator. So let's say the battery takes the energy from the grid, but as soon as the battery gets too low, the generator will turn on and will recharge the battery again until it's full, and then will turn off. I will also show to you this in a case we did. This is in Rotterdam, where there was a refugee ship. These ships are usually cruise ships that they just go on for holiday, but now they are stationary, in the water, but in the harbor, and they basically make a hotel out of it for their refugees. So there's becoming a crew catering on there. There's food for all the people on the ship. So the load, of course, increases quite much. Because you're in the middle of a city, generators aren't an option just by itself, because they create a lot of noise, and also next to our home it smells. So what we did there is a little bit of grid available, but it wasn't enough to supply the full load of the ship. So we put a generator there, but because we put a battery there together with a generator and using the grid, we reduced the running hours of the generator quite much. How does that look in our data projects? Is you can see the state of charge going down here. That's basically because the load is too high. So you can see the input power over here. We're getting almost 60 kilowatts from the grid, but you still see that the state of charge is dropping down. So that means the grid is doesn't have enough capacity to supply the full load. So you see at this point, we turn on a generator. And the generator, in this case, is in fixed power on the output. So it just pushes a fixed amount of powers back into the battery. So that's why you see on the output over here that first we are delivering around 45 kilowatts. And then the load drops over here, and there's negative energy being pushed into the battery, which causes the state of charge to go up here again. And we just keep repeating that. What we also did in this case is we installed a night mode on here. Because we were in their city, the generator wasn't allowed to be turned on during the night. So what we do is we make sure that the battery is full before 10 o'clock, and then the generator doesn't get turned on the full night and only gets turned on when it's morning again. This results in grid optimization, but because we also were working with the battery, we reduced a lot of running hours on the generator, which is of course results in diesel savings, emission savings, which also results in cost savings, because the less diesel you use, of course, the less cost you have. And it also results, like Robin also talked already about, is less maintenance. So which also results back in cost. And on the bottom, I've added a screenshot of the report that came with us through our software. And you can see that in a week time, we saved a lot of diesel hours, a lot of fuel saved. So the liters diesel you saved, the CO2 and the NOx. And you can also see, which is, I think, really nice on the top right of the bottom right here, is that you can see how much energy we actually got from the grid connection and how much energy we got from the generator. And of course, because we're working with a battery, we could use the generator at its most efficient rate to supply these last couple of kilowatt hours. So you can see that the 62% of the energy is coming from the grid, and then 38% is coming from the generator. I will now pass it back to Robin. He will talk about the last standard setup.
So what we've just seen with the other three situations that we've talked about, all the energy is passing through the battery. What if the battery, the copper bus bar or the connections on the battery are not big enough for the entirety of the energy? Well, we can then use our system, which is called Grid Boost, in which we connect the input of the battery parallel on a bus. That means that suddenly, where first the input of the battery towards the output of the battery was the limit, being 250 kilowatts, 400 amps coming in, 250 kilowatts, 400 amps coming from the inverter, stacking to 800, 500 on the output, would have been the limit of the system. But if you then need more energy, so let's say that this grid connection is a multiple MVA connection, obviously that's not going to pass through the battery unless you have a very interesting warm puddle of copper at the bottom of the machine. That's a problem. So we instead of doing that, we designed a system which will parallel connect a battery to this connection. Obviously, then we still need to know how much energy is being consumed or being drawn from this grid. So this is where we use our external meter or one of the existing meters which are already at the point of coupling, and integrate that into our EMS, and then via this part send commands to the battery to draw or push energy out of its storage capacity. So what does that mean? So that wherever we place the meter, we then tell the battery system, the EMS battery system, the EMS in the battery system, what the limits are at the point of coupling on the meter, and it will try to keep these limits set. So I have a very nice case to show you guys. Obviously, when we're doing this and we were in parallel, the limit is not one battery anymore. You can do a multiple of batteries, because the question is not how much capacity is the battery system, but how big is your bus. That's suddenly the limit in the system. So we were on a location where they had a seasonal need during November, December at a warehousing estate, where they had a grid of a 3 MVA grid, and they required another 1.25 kilowatts of power and 2 megawatt hours of battery capacity. So we put down 5 systems. So how do we find the situation? Before they contacted us, they had a 500 kVA set that just started pushing on a timer onto that bus bar to reduce the load coming from the warehouse onto the grid. And then they would run it on a timer going from moment A to moment B. So we said, well, we can do something better. We can utilize the entirety of the grid and then just use our measurement device, our external meter, and then connect that to our cluster of batteries of 5 and make the EMS push and pull on that bus bar along as the measurement system tells us when to do that. So I took out a little bit of the measuring data from one single battery, and because the cluster is doing the same, the same on every battery will have been doing the same amount of power. So if you look here, you see the state of charge. So that's the stored capacity in this period of time. So this is about 2 weeks, and you can see that that there's quite a trend trend coming back. So it's very it's on the same times of the day that the energy is extra needed. And what you then also can see very clearly is how after a period of using energy, we then charge the battery when the demand on demand diminishes. We then utilize the excess energy on the grid to charge the battery again back. So this is what you see here. This is in the same time scale where the used battery is the state of charge deplete is when the battery is assisting the grid, and the state of charge increases when there is surplus energy available on this specific grid connection. So that means that we had 0 imported energy from somewhere else, and I mean that there's no generators. Which will and this has been running for the last 2 or 3 years for 2 to 3 months, a little bit depending on the weather. Going from September, November, December. So that's my story from the grid boost setup.
Why like going back a little bit to the rest of the story, why would hybrid be a better a setup than only a generator, for example?
So a little bit of that. So there's a technical answer to this. If you look at the energy efficiency of a internal combustion engine or of most energy conversion systems, there's a sweet spot where the amount of fuel is converted in the most efficient way, right? That means you put in a potential energy of so many kilowatts and you get out so many kilowatts of real energy at the end. Well, you can imagine if you have a generator, it has a idling consumption. Let's say that it's for, and we are not a generator company, so I don't know the exact numbers, but let's say that it's for a 300 kVA generator, it's 30 liters of diesel an hour, give or take. That means that this 30 liters of diesel every hour is producing exactly 0 usable energy. It's just to keep the machine alive and have a electrical grid available. Then you can imagine that if you increase the load, that the first 30 or 40% still will have a very low efficiency rate because you're still using the first 20 liters per hour to produce, to just keep the system alive, and everything on top of that is producing energy. And it happens to be, and you can, and then what happens is that when the generator runs at about 80%, 70 to 80%, it's at the top of the efficiency curve. So we utilize this place between 70 and 80%, preferably, and then either shut it down. What we also do is then, once the load actually exceeds more than 50% of the capacity of the generator, we then start the generator anyway, because otherwise it makes no sense anymore to do a cycling as opposed to a peak shaving setup. What does that then mean in real life? If you own a car and you try to drive that around within the city, accelerating and braking, or if you drive on the highway where you just put it at a fixed speed, click it into the cruise control, and if you then measure your fuel consumption, you will note that on the highway you're actually more efficient while going faster than you are in the city if you look at the miles traveled. And we utilize this as well, because what you could also see during in the graphs is that once we will filter out all of the accelerating and braking, so all the peaks and troughs of the load will all be filtered out towards the generator and be handled with by the battery, because the battery has a infinitely faster response time than a massive rotating mass.
Yeah.
And that helps us enormously.
And that also results in cost savings, right? So we use the generator at its most efficient rate, so we get the most kilowatt hours from a liter diesel, but we also only turn the generator on when it's needed. So you reduce your running hours, which means there's no inefficient way of using the generator. That means less diesel cost, less diesel consumption results in diesel cost. So that's also a reason why commercial-wise you should, why a battery could be really interesting.
Yeah, and the interesting hidden costs of generators. I mean, everybody knows that we need to go to stage 5 systems. And
what's the stage 5 system?
So that's when you use urea or AdBlue to clean the exhaust. The exhaust emissions, but this needs this needs the system to run at load, otherwise it won't work. So like I said, we run the systems preferably between 70 and 80%, and if the load is high, the generator will run from power from 50%
and 80%,
because that's where the efficiency curve is highest.
Okay.
So the most kilowatt hours returned from a liter of diesel.
Nice that you're talking about this, because I have one question from the audience that's related to this. What's the average efficiency for these diesel generators?
So that's a question that's really hard to answer. Like I said, we don't own these machines. It's highly dependent on the size of the generator, the age of the generator, and the maintenance done on this. We of course use a rule of thumb, which says 3.5 kilowatt hours per liter of diesel at 80% utilization of your generator. If you have a more modern system, which is well maintained, it'll be higher. If you have a older system, which is not so well maintained, it'll be lower. But rule of thumb.
Right. Then there's another question from the audience. As you can see, we've arrived at the Q&A. With Grid Boost, can it also be hybridized to help cope with demand?
Yes. So what you can use is yes, you can. We can obviously ask a other source to provide power at state of charge. It does mean that the power source needs to be able to do a fixed power setting or a mains parallel setup. You can imagine if you have a system that is using either frequency or voltage control to determine the power that it needs to deliver. Well, if you're against the grid, you're not moving the frequency anywhere, nor are you moving the voltage significantly enough to do that. So you use a fixed power or mains parallel mode on your energy source.
Right, great. And what I was wondering myself is when we look back at the MRI project, I'm wondering what you think is the most interesting about that, because you see obviously a sort of evolution going on. I think that's also one of the benefits about working with us. But yeah.
So the interesting part here is that we scale this. This is zoomed out a little bit, so we're not really seeing. We've in the scaling out. In the scaling out on the graphs, we're losing the fine-grained details of the high peaks which are going out. What you see if you really zoom into here is that the inrush is nearly 200 amps. This is too much for the 125 amp connection to keep alive. But because we are using our battery in between, we filter that out. We supply that extra energy from our storage device, and we keep the load on the supply really low. And then what you see is that you're very often scaling things for this peak power demand, but that the nominal load is fractions of that peak power demand. And then by using measurement devices, we can filter those out.
Nominal load is what you...
The average load over a period of time. Yeah.
Right. Another question from the audience. In the grid boost data, the state of charge is dropping below 15%. What is the lowest state of charge for your batteries?
So our older systems, we really switch them off at 5. That's because if you then want to recover, you still need a little bit of space for recoverance. So that's what it is.
Right.
Absolute minimum is 5. We tend to switch them off at 10 to give us a little bit of slack to fire them up. It's the same when you have a well-used fuel tank. You don't want to completely deplete that as well, because then you need to clear out and filter out all the crud that goes through the system. And obviously that's not the same here, but it gives you all sorts of starter problems if you go all the way to 0.
All right. You have anything to add, or?
No, he's right on.
Great. Well, then another question from the audience. How much cheaper is a hybrid system when you factor in the rental costs of the generator and the battery compared to the cost of the generator alone?
Right. Well, so this is a really, really interesting question. This really depends on your load profile. So what we now see, especially with these diesel prices right now, is that usually we get the business case around. So even though you've got an additional asset, which also has a rental price, of course, we still tend to be cheaper than just a diesel generator. The main thing where you can save diesel costs is the way your power profile is being made. So the more peaks you have, so the higher the peaks and the lower your average load, so the more variable load you have, the more interesting it becomes to actually see the business case coming around, so that the hybrid setup is going to be cheaper than just a conventional diesel setup. This is really interesting because we can definitely help you guys out with calculating this. So if we've got a load profile, we can calculate this and see upfront how much diesel you're going to save with using a battery and a diesel generator. But usually I think, especially now with these diesel prices, we tend to get these business case around quite easily, especially if your load has lots of high peaks. So if your load is really constant, it could be even, but you'd have some additional benefits of using a hybrid setup instead of a just a diesel generator setup. But cost-wise, yeah, it's getting better and better.
And there's two strong arguments. There's of course the actual running cost, liters of diesel not being burned, but there's also a very large part, the hidden cost, which is a lot more difficult to quantify, but this is in maintenance. And especially if you're talking about stage 5 systems, most of them are spec'd from the manufacturer to be at least at 50% load. Well, if the load is only 10% nominal of the generator, you're going to run into all sorts of problems, where a system like this will just take that problem and make it go away. And then the amount of costs saved in swapping out and tearing apart the generator to replace the exhaust is humongous.
Yep.
So do you also expect that this is where the trend is going? If people realize this, more batteries, less diesel. How do you guys see this in the near future and long term?
Yes, so I think you've got two views on this. So you've got a technical view on this. So like Robin is telling us about, is like technically making the system work and being redundant. So having more or less downtime. That's one point. And then on the other side, you've got financially benefits on this. And I think the financial benefits is, of course, a way better drive usually. So it started, of course, with the technical benefits, but now it's shifting to the financial benefits. And yeah, we can just show customers, and they can also see that back into the data, how much cost they are saving. So, and of course, everyone wants to spend less money. So the trend's going to be way quicker than before, especially with these diesel prices right now. Is if you use a battery, you still pay a lot for the rental price of a battery together with a generator. But even though you've got an additional asset, you're cheaper off than using just a diesel generator. So I think this trend is going to be way quicker.
Now, if you calculate it, you're saving 50% on your running hours. With, we just said, is about 20 liters of diesel an hour, times, what is it, 2.5 euros for a liter diesel. Let's say it's 2. So let's say that's 10 hours in a day that the thing's running at stationary for 7 days. Well, that's the margin you have to rent the extra stuff, and then all the extra diesel saving comes on top of that.
Does this also mean that because before renting a battery was usually only beneficial for long-term projects, but with recent developments, could you assume that if it's now also more beneficial or becoming more beneficial for?
Well, starting and stopping a project has a fixed price, right? So if the reduction in cost is bigger on a daily basis, then shorter things get more interesting as well, because if you're going to spend 2,000 euros, I don't know, to get a system transported and installed, but you're saving only 500 euros a week, then you need 4 weeks of running time. But if you're saving 1,000 euros, then suddenly 2 weeks is interesting.
Yeah. Another question from our own team, and it's from Iris, and it's good that she reminds us of this. She asks us, is there an easy way to calculate the difference between a generator only versus a battery setup, like a tool? Referring to our calculation tool that we recently launched.
Really, really nice is we've got our own tool where we can actually upload a power profile through 50-minute data, or we can create our own power profile in our tool, and we can compare the conventional setup you would usually have to use there and give the rental cost there, and compare it to a hybrid solution, so a generator with our battery. And you can see in one nice overview how much diesel you're going to save, how much cost you're going to save, how much CO2 emissions you're going to save. So definitely, if you have any projects where you think, oh, maybe this is interesting, send us some data and we can get that in our tool and show you what you could actually be saving.